Thank you for having me. It's a pleasure to be back in Madison. My name is Douglas Thain. I hail from the University of Notre Dame. And today I want to talk about a piece of software that we've been developing that's called TaskVine, and how we've been using it to build high throughput function-oriented workflows. And hopefully I'll define, let's see, which of the buttons do I need on this? Okay, good. So we're big users of HT24 at Notre Dame. We have a pretty good sized pool that backfills our HPC facility of about 20,000 cores. And it's sort of an interesting place to work because given, depending on the day and the time of the season, sometimes the HT24 pool has almost the whole facility available, because it turns out that nobody does any computing after exams are over, at least on the HPC side of things. And then things get very interesting at the end of the semester because the pool sort of shrinks and shrinks and shrinks and then all of a sudden comes back. But that's good because that gives us an opportunity to figure out how to be opportunistic with the resources available. Now, my work over the last couple of years with my lab has been in designing tools that help people organize the work that they want to do in order to do high throughput computing. And so if you had the misfortune of hearing me here over the last couple of years, I probably talked about Makeflow, which is a way to build big DAGs using a make sort of syntax. It also does a JSON kind of thing. You may have heard me talk about WorkQ, which is a way of constructing big master worker applications. And today I want to talk about TaskVine, which is a system for data-intensive workflows, and in particular function-oriented workflows is the new thing this time around. So TaskVine is a system for executing data-intensive scientific workflows on clusters, clouds, and grids. Do we say grids anymore? Just clusters and clouds. From very small to massive scale. We want to make it easy to prototype something on your laptop and then make the jump to your high throughput computing cluster. And what's interesting about TaskVine is that it controls both the computation and the storage capability of a large number of workers, striving to carefully manage, transfer, and reuse data and software wherever possible. And the storage bit is key. In a big cluster, all of your nodes have some kind of local storage on them, whether it's a disk or an SSD or an NVMe or what have you. They all have some reasonable capability. It's not unusual to have a terabyte of storage on every single node of your cluster. And that collective storage capability is pretty substantial, both in terms of total capacity as well as performance. And so a TaskVine application looks like this. The user is going to write an application over here on the left-hand side in which they define tasks and data to a manager process. The manager process usually sits on the front end of the cluster and talks to workers that we have submitted to our HT24 pool. And where the workers run, they manage the computation, yes, but they also manage the storage on each of those nodes, and they all talk to each other as well as outside resources. So if you're building a workflow that has substantial data needs, a big advantage of TaskVine is that it coordinates the movement of data from outside sources into the cluster, between the nodes in the cluster, and then back out again when you're done. And furthermore, it's often the case that the software is a significant data resource in terms of getting applications to work. If you use big Python libraries, if you use TensorFlow or PyTorch or something like that, oftentimes your biggest problem in using the cluster is just getting the software to the nodes and using it effectively. And so TaskVine manages that as part of your workflow. If we zoom into a node of a TaskVine worker, it looks something like this. So over there, we still have the application in the manager. And here we have a zoom in on one worker. And a given worker manages the memory and the CPUs and the GPUs available. And then it has a cache directory, that's that stripe in the middle, where it stores all the assets that are being used by the tasks on that worker. And so each of the assets are kept in this cache directory under a unique content-derived name. And as the boxes there sort of suggest, they can be materialized in place, or they could be something awaiting transfer. So if you had something that was coming from an outside source there, that little blue box over on the left is a pending transfer waiting to come in. And now, much like HT24, each task runs in a sandbox, so it has a private namespace. And we link in the inputs and the outputs so that files can appear in different ways to different tasks. So in this example here, let's see, I can. This task here is consuming this data that came from a URL. It's producing an output file, which then gets stored in the cache directory. And a given file can appear as different names. So to this task, this is an output, but to this task, it appears as input.txt.
Doug, do you assume that the worker has access to the entire node, or you assume that there are different workers that are running on the same node?
So we assume that a worker is running in an allocation that is given to it by HTCondor.
Yes.
In the most efficient case, the worker has
everything,
the whole node, but it still works if you end up.
So how do you allocate the storage to the worker, and how much do you ask?
Right to the heart of the matter. Yes, this is a challenging problem.
Really?
It's
good.
tough. It's
Thank you.
Problem.
Okay.
It's a challenging problem because the operating system doesn't want to cooperate with us, and so it works best.
And how do you? Okay, yeah. Fine. So
if you really want it enforced, we'll make a new file system with a loopback device and mount it through, and then you have to be root, and everybody suffers.
Yeah.
Yeah.
But it is also a question of how do you even decide how much to request for the worker. So if you're multi-tenant, so a worker goes out, let's assume everyone is nice and you don't have to enforce anything. Yeah. But how much do you tell Tony that he has storage on his worker has storage on? Okay, keep going.
Right, okay, so to give you just a sense of how this works, I'm not going to talk you through the whole API here, but the idea is in order to write a TaskVine program, first you declare your assets, right? So if you have files that are inputs, you're going to declare it as a file. If you have some literal data, you declare it as a buffer. If you have some external data, you declare it as a URL. If you have some temporary file that just needs to exist in the cluster between two tasks, you declare that. And then there's some interesting transformations you can perform on that data. All right, so you declare your data. And then you declare your tasks. And if you sort of squint, this looks kind of like a Condor submit file, right? You've got a command to run, you set the resources, and you attach those things that you declared before to the namespace of your task. All right? So you declare your files, you declare your tasks, and you go and submit them, and they run. If you have some Python tasks that you want to run, we can wrap this up nicely so you can say, all right, here's the name of a function, and it's parameters that we want to pass in, and we can treat that as a task as well. Now, if you are, what's the word I'm looking for here? Diligent? If you are diligent, you can make big stuff this way, right? So I could declare a whole bunch of files, and I could declare a whole bunch of tasks, and I can connect them together, and I can make a big old DAG like this, and TaskVine will happily run that for you. And I can spend about 2 hours talking about all the ways we can optimize the data transfer and the movement of that DAG. That's kind of fun, but that's not where I want to go today. So you can do this sort of stuff, or maybe you can write a program to generate your DAG, but if you've done some DAG processing, you know this gets old after a while. Now, where I want to go today is to the next slide. I'll talk about the difference between tasks and functions. All right, so if we think about, I'm going to define a task in the usual sense here as a program that you want to run. A task is a thing that has a start and an end. It has some input files, you invoke it, it runs, and then when it's done, you tear it down and you throw it away because that's yesterday's news and you're all done. And in some sense, this is good, right? Because we want to be able to have a clean setup and a clean teardown for everything that we do. But for many of the applications that we're exploring now, it makes a lot more sense to think about functions, or as we like to call them, libraries and functions as separate things. And so a key abstraction in TaskVine is the notion of a library task. A library task is something we send out to a node that contains some function code, and it comes to life, and it stays there. And it can load its state into memory, it can load its code, it can do whatever initialization it needs to do, and then you can send multiple invocations to that function. You can get multiple results back from that function, and that thing stays alive. Now, this is a lot like serverless. Who's heard the term serverless? You've all heard the term. I hate the term serverless. It makes no sense. So I'm going to talk about libraries and functions anyway, but if you prefer to use the word serverless, we can still be friends. All right, so we can now create workflows of functions using this model. And so the way that this works in TaskVine is you write a little Python program that contains some functions. Here's a sum and a multiply. You create a library out of those functions and install it into the system. And now the way you can think about it is you have all these workers now in which the library is now run on demand, and it is installed in those workers and ready to be invoked just like that. And so now, right? And so now we can define tasks that are calls to those functions. Now you'll notice here we invoke a library by name, not by symbol, right? We invoke a function by name and then pass in the immediate values. And now we can send these function invocations out to these workers. And it has huge benefits, right? So if you're using some expensive Python library like TensorFlow or what have you, you're going to save something like a gigabyte of loading Python libraries every time you do this. You're going to save 30,000 metadata system calls if Python doesn't have to search through the file system, what have you. And you're going to save a bunch of latency in terms of setting all this up. All right, now, if you want to, again, you can go back and construct all this stuff by hand, right? So if you want to define function call, function call, data, you can do that. But what's more interesting is we can use some higher level libraries to generate this stuff. And I'm so excited, every time I put this slide up, I get excited. I'm so excited about this. Ben here built this system in which he connected Dask with TaskVine. Now, Dask is a Python framework for performing parallel computations. It lets you work on data structures, arrays, matrices, maps, what have you. And it lets you use standard accelerator tools, TensorFlow and PyTorch and NumPy and all that sort of stuff. And this is a complete Dask program right here that uses, couldn't resist the term TaskVine, I'm sorry, uses TaskVine to connect Dask to TaskVine. This is a complete program here which processes an input data set. This is a physics data set that's coming from an XRD server. And it's doing a simple computation here. It's summing up some stuff and producing some histograms. But what happens internally is it creates this big DAG of stuff and then runs it. And the reason I'm so excited about this slide is it combines two nerdly passions of mine, right? So it's distributed computing, but it's also a compiler. Because what we have here is a program that expresses concurrency, and we have a compiler that turns it into an intermediate representation that we're going to go run on a cluster. And there's so many opportunities here that we have hardly touched yet, because there's so much fun we can have. We can do loop unrolling, we can do fusion, we can do instruction selection, we can do instruction scheduling. We can take that whole book, the whole Dragon book, and open up every page and say, oh, we did this in traditional compilers. It's going to be a little different in distributed computing, but we can take advantage of it. So what we're doing here is effectively building a compiler for programs that turns them into something that can run efficiently on a cluster. All right, now where can we use this? Well, as I'm sure many of you are here, we have some friends in physics. And what they are doing is performing data analysis, late-stage data analysis for CMS. Now, what I'm talking about here is not the big stuff that happens in the front end in the WLCG to do all the shared processing, but the stuff that happens at the very end when you have one graduate student who's interested in one particular interaction that only happens with electrons after midnight, and they're searching for that one particular thing. And so they need to consume something like a terabyte of data, and they're going to generate something like 10,000 tasks. They're going to search for some process, output some data, and then accumulate some sort of histogram here. And so, the state of this about a year ago is that our friends were running on about 2,400 cores, 17,000 tasks, and they could run their whole thing in about an hour. Now, in the old days, if I told you we're running 2,400 cores for an hour, you'd say, gosh darn it, that's high throughput computing. And we'd feel pretty good about that. But for our friends, it's not fast enough. Because, of course, this means you can only do it a few times a day. And if you're a graduate student developing a code, you make one mistake in that final step, and an hour goes by and nothing happens. And so can we do it faster? And I'm missing a slide here. And we've really struggled with this because they've turned all the knobs that they can turn in order to make it better. They tried to make more jobs shorter, but that didn't help because we had too much overhead. They tried to have fewer longer jobs, but then we don't have enough concurrency. They tried chopping the data smaller, they tried chopping the data bigger, they tried bigger workers, they tried smaller. Nothing changes. An hour was the iron bottleneck, and the reason was the overhead and all the things that they need to do. So what we did here is we did sort of a careful study of evolving from an old system to a new system. And in our old system here, we're doing this whole Dask thing, and on our old system, WorkQ, which is an old friend, but we could improve upon it, and it's all their data sitting on top of Hadoop. Now, every time I show this slide, I know everybody jumps up and says, Hadoop, that's old stinky potatoes. Nobody uses that anymore. That's holding your whole system back. And we weren't sure, but that's what our HPC people said too. And we said, what should you do instead? They said, you should spend $10 million on a new HPC file system. I said, I don't have $10 million on a new HPC file system. And they said, after a while, fine, we have $10 million and the whole campus needs it. So we're going to throw away that whole stinky thing and we're going to use a new $10 million file system. And so we dropped in VAST and it got 5% faster. Now, this is not a complaint about VAST. So if there's anybody here who likes VAST, it's pretty cool. It's highly performant. It's low latency. It seems to be reliable. We're very happy with VAST overall. But a $10 million file system was not the solution to our problem, because the problem was really the structure of our application, not the hardware that we're running on. So the next step we did is we swapped out WorkQ with TaskVine. And in the things I've shown you so far here, the benefit of TaskVine is it uses the local storage on each node. And once we started using the local storage on each node, we could cache recently used things. We didn't have to move things to the shared file system and then back out in order to take advantage of them. We could keep local data local. And here we started to see a real difference where using the same hardware, same scale, same everything, but just swapping out TaskVine for WorkQ, we got on the order of 4 to 5 times faster. That's pretty good. But we're not done yet, because in this iteration, TaskVine is still using ordinary tasks where we start a Python process and we stop a Python process. We converted this to take the functions out of the application, convert them into these libraries and functions, and now we've got this down to 272 seconds, which is 13 times faster, which is enormous for the person who is doing data analysis. All right, so how did it get better? Well, one reason behind it getting better is that we have data transfer between all the workers. And so this heat map here shows all the different transfers between all the workers in a particular run. But the real killer was moving from tasks to functions. In the old way here, when we scaled up from 20 workers to 200 workers, and we're using tasks, the blue lines here show when the CPUs are actually running on your code. And you can see there's big gaps between each of those computations, and the reason is all this overhead of starting and stopping and loading and storing, and so we're wasting our time in the cluster. When we move to functions, we're able to eliminate all of that overhead, compact everything in, and get the whole thing done. All right, so I see I'm up against time here. So what we did here is we stacked Dask on top of TaskVine on top of HT Condor, and this is, if you like, our compiler stack for running applications at very large scale. But we can do it with other sorts of workflow engines. And so we've been working with colleagues from the University of Chicago to do this with Parcel. And it turns out to have a really big impact on machine learning applications. Now, why is this? Well, you have a big data set. And where does that data set want to live? It wants to live in the GPU. You don't want to write a workflow in which you're constantly moving things in and out of the GPU. If we can design it to use libraries and functions, we can keep the data not only on the worker, not only on disk, not only in memory, but in the GPU, and keep going back to it again and again and again. And so what this graph shows here is an inference application where L3 here, this orange curve, was the time to execute, just sort of doing it the standard HPC way. This here was keeping stuff on disk, and this here is keeping stuff in memory in the GPU. And so it has enormous impact on how we go. All right, I think I'm out of time. So just sort of the status of TaskVine. TaskVine is a component of the cooperative computing tools. Well, it's release 7.11.1. That's of our whole stuff. That's about the 3rd release of TaskVine was made this month. This is research software, but we have an engineering process. We don't have the army of staff that Condor has, but we're pretty careful with the stuff, and we want it to work, and we're interested in finding new users. And so if this sounds interesting, we'd love to talk to you and see if we can collaborate on new applications and challenges. If you want to have some fun, you can go to read the docs or you can conda install it. I want to thank all the members of my team and my collaborators, as well as the NSF for supporting this work. And thank you very much.